Hey, welcome back to Chemistry with Mrs. Mays. Today we're taking a closer look at quantum mechanics. This can be complex, so you have to pay close attention. Remember, Bohr is the one that did the photoelectric effect, and he said electrons are in certain energy levels. And while this was a big step forward, the Bohr model was only useful in predicting the energies of spectral lines for atoms that had only one electron. And that's limited to hydrogen, or certain ionized atoms, like maybe helium, if we remove one of its electrons. So it had limited application. The Bohr model was just not sufficient. There was more to the story. Then comes Louis de Broglie. De Broglie proposed that electrons in specific orbits produce standing waves at specific wavelengths, energies, and frequencies. And the standing wave looks like this, where you would have the node and the antinode, where this is a node and this part is the antinode. You may have studied some of this when you learned about sound in physics class. We'd already talked about how electrons are particles, but if electron was simply behaving as a charged particle, then it would fall into the nucleus, which was positively charged, while the electron is negatively charged because of Newton's second law. The electrical force between a positive and a negative charge, since it's an attractive force, it would cause them to accelerate towards one another. And that just couldn't be. We would not have atoms. We wouldn't have any matter in the universe. Another equation, besides Newton's second law, is the electrical force described by Coulomb's law. The charge of the first particle, or the positive particle, multiplied by the charge of the negative particle, divided by the square of the distance between them, or the radius between them. And that we can set equal to Newton's second law, and we would be able to describe the attractive force between a positive charge and a negative charge. But electrons in atoms aren't just simply particles. They're also waves, and waves don't follow Newton's second law. Schrödinger had to invent a new equation for wave mechanics. H times psi equals E times psi. It looks very different from Newton's second law, but this describes mechanics for waves. The mathematics here are not something we'll get into in the class, but this is where Schrödinger started with his wave mechanics equations. And this gave birth to the field of quantum mechanics. Quantum mechanics is a branch of physics which provides a mathematical description of wave-particle duality, where we know that matter is both a wave and it's a particle, so we have to join both ideas together. So we can successfully explain the idea of varying energy states in complex atoms and molecules, not just simple atoms like hydrogen. We also can explain the relative brightness of the spectral lines in the atomic emission spectrum. And it's because matter and light both have this property of acting like a particle and a wave. It's both. Remember, electromagnetic waves are made up of oscillating magnetic and electrical fields. So what is oscillating in an electron, or in a matter wave? The wave function, psi, describes the state and behavior of an electron. The two fields of the wave are noted in blue and red in this animation. Each wave frequency is proportional to the possible energy level of the oscillator. So let's watch these oscillate for a bit. So a light wave is made up of oscillating electric and magnetic fields, but the wave function for an electron is described by the possible energy levels of the electron, or whatever particle of matter it is that we're looking at. And you can see in the animation the nodes and the antinodes that form as these particles oscillate. So rather than finding an electron like, oh, there it is, we use the square of the wave function at any point will be proportional to the number of electrons that are expected to be there. So we're using probability and statistics rather than just saying, oh, that's where it is. We can say that's probably where it is. So xi squared is proportional to the number of electrons. And for a single electron, the wave function is the probability of finding an electron at that point. So xi corresponds to the probability of finding a single electron, whereas xi squared gives us the number of electrons expected to be found at any point. So this kind of seems strange at first, doesn't it? The world of Newtonian mechanics, classical mechanics that you learned in physics, is a deterministic world. If you know the forces on an object and its initial velocity, we can predict with a high degree of accuracy where that object will go. But quantum mechanics is very different. We can predict what most electrons will do on average. But really, we have no idea what any individual electron will do. And part of this was described by Werner Heisenberg. In the Heisenberg uncertainty principle, we learned that there's an inherent limit to measurement. The measurements can only be accurate to a certain degree. And it's not because of the limitations of our instruments, but rather it's due to wave-particle duality. And in particular, due to the interaction between the observing equipment and the object that is being observed. One good example is to see what happens when the principal comes to observe a classroom. The principal walks in the door to see how the classroom is functioning, but because the principal is there, everything changes, right? The students change their behavior and the teachers change their behavior, and now the principal can't really observe what he's hoping to see, or what she is hoping to see, because the act of observing changes what we're trying to observe in itself. So consider this experiment. Student A and student B are both blindfolded and given a hockey stick. They're placed in identical airplane hangars, a really big empty space. Somewhere in the hangar with student A is a school bus. And somewhere in the hangar with student B is just a small balloon floating around at eye level. Both students are told to find the object in their hangar by swinging their hockey stick as fast as they can until they hit the object. As soon as they find it, they must stop at the place where they encounter the object. Could you imagine trying to do this experiment? Who do you think is going to find their object and be more accurate? Which student's final position will more accurately reflect the final location of the object they are looking for? Why do you think this is true? I want to check your answers when you come to class, so write down your thoughts about this and show me what you've written when you come to class. So Heisenberg put two things together. First thing is position. Where is the object? The other thing was its momentum, or velocity times mass. Like, where is it and how fast is it going? So we have a combination of these two uncertainties led to this equation that the uncertainty in the position multiplied by the uncertainty in the momentum would be somewhere proportional or nearly equivalent to Planck's constant h, where x is describing position and p is describing momentum, and h is now known as Planck's constant, the number 6.63 times 10 to the negative 34 joules times seconds. Specifically, this is called the Heisenberg uncertainty principle. It tells us that the position and the momentum of a particle cannot both be known at the same time with precision. Now we come back to the probability of finding an electron in any given space. Since we cannot say exactly where the electron is, the Bohr picture of the atom with its electrons in neat orbits in circles around the nucleus, this cannot be correct because we can't really say exactly where the electron is. We can only say where it is likely to be. So quantum theory describes an electron probability distribution. Here's the distribution for beryllium, boron, and carbon. In this picture, what we see is a dot for every time we have the chance of finding an electron, or the probability, that is, of finding an electron somewhere in that region of space. So the dot represents the probability of finding an electron is represented by the density of dots at that location. So we're not likely to find an electron through this axis, but going through this way, we see a large electron density here and here, so we know it's more likely to find electrons in those regions of space. That's what we know now as an orbital, a region of space where there's a high probability of finding an electron. We'll practice in class. See you soon.